I'm Gurashish. I work for Bloomreach. I'm a member of technical staff over there. We're a company based in Mountain View, mostly B2B, working with e-commerce merchants. My talk today is about Cassandra Compute Cloud, on how to scale Cassandra for large-scale EMR jobs. What am I going to talk about? Mainly how to scale the infrastructure to support elastic MapReduce jobs. At the same time, how do we guarantee SLAs to backend applications, mainly again, these EMR jobs. And on the same infrastructure, how do we ensure that we can have a reasonable amount of SLA for latency? We like to measure in the 95th percentile, but you can extend that to 99, 90, any number you like. And of course, this is all based on Cassandra 2.0, and we're using vNodes. I'm going to break my talk into basically three big areas. One is we'll talk about the application requirements. The design usually revolves around exactly what your application needs. I think it's important to understand our particular use case to get an idea why we went with the solutions we did. And some of the major issues we encountered, we started naively in some sense, and we learned along the way. And then we'll talk about the solutions that we came up with. So application requirements. We have a lot of backend elastic MapReduce jobs. They perform scans, they perform random lookups, a lot of writes. There are many heterogeneous applications, multiple applications with different expectations, different level of throughput, different scale size. And typically with these MapReduce jobs, we see very heavy peak load. And in some sense, it makes sense because you're writing a cascading flow starting from a source tap, then a bunch of operations, then a sync. And the source is when you see a very heavy read load on the cluster. Sync is when you're going to see a very heavy write load. In between those operations is all in Hadoop. And that tends to generate, maybe the job ran for 3 hours, but for half an hour you saw very heavy peak loads. One of the requirements for us, being part of an e-commerce environment, is we have to be always available for these backend jobs. That is, we can't take a downtime. We cannot say that, well, we need a maintenance period because we need to expand capacity or add nodes. These jobs, they have to run all the time. Most of the time, they are driven by pricing, inventory, and all, so we can't say that on this day you're not going to get pricing updates. We have front-end applications, which are mostly lookups. There are no scans. The typical use case is we build the data from the backend applications. It needs to be made available to the front-end applications almost immediately. And of course, we want really low latencies. Last one I mentioned is the developer support. By developer support, I mean when you have a lot of developers working on a lot of big data applications, the one thing that we want to make sure everybody has access to is that if you design a system, you should be able to test it at the full scale. It's easy to build something that just works for, let's say, 1,000 products or 10,000 products. It's a whole different ballgame when you actually deploy in production and it falls apart at 100 million products. So we want all developers to have very easy access. Now, the traditional mechanism is you build a staging cluster, but when your data is so big, your staging cluster becomes as large as your production, and that adds to cost. And again, the same thing applies. Can you guarantee latencies on staging? And if you move them to production, then developers themselves have very unpredictable load. We're getting close to product launch, and now suddenly everybody's running huge jobs, and that you can't react with something like Cassandra that quickly. So basically what I'm trying to point to is that in this kind of environment, we see very unexpected load. Trying to plan for it is not that easy. You can plan for something like holidays coming, and there's a front-end size planning. That's well understood. You know your past traffic. You can multiply by 10x and go ahead with that. But on a day-to-day basis, from a regular use cases, it's not that easy. And in a fast-paced environment where we are expanding quickly, which is a good problem to have, I would say, you have to be prepared to scale very quickly. So how do we start? We started with a single Cassandra cluster, when we went with the network topology strategy. If we call it a front-end data center and a back-end data center, the EMR jobs, they basically access the back-end data center. We were using the standard native protocol, the DataStax Java driver. We did the right things with the round-robin policy and token-aware policy and data center-aware policy. So made sure that the back-end jobs, they go to the back-end data center, and the front-end applications only talk to the front-end data center. And it seemed to work. We had other options, which was we could have built a separate cluster for the front end and a separate cluster for the back end. But then we'll have to, if you recall, I mentioned that the front end applications want to get the data that the back end applications load right away in real time. And if we had separate clusters, then we'll have to build that replication and maintain the consistency between the two data sets ourselves. And that'll be just another set of problems. And we really like the Cassandra replication strategy, that it takes care of all those things for us. So, like I mentioned, the front-end isolation, it seems to work pretty well. That the load on the back end is driven by mainly the back-end nodes. The front end sit happy, no issues over there. But what happens if your backend is under very heavy load? Let's say your EMR jobs, somebody just ran too many EMR jobs. And now this is a bad situation to be, because your backend is basically down. But there is no concept of front end and back end. It's basically multi-data center. And it's a local data center versus a remote data center. If you can't find the nodes in the local data center, you're going to fall back to the remote data center. But what happened? An outage on my back end translated to an outage to my front end. I need higher, stricter SLAs on the front end. We could have tolerated a back end failure, but translating that to a front end spike in latencies is much more severe problem. Another issue for front end latencies, we discovered that at least in our use case, our data is disproportionately write heavy. We have on the front end data center, we have too many writes coming in from the back end. And we have reasonable amount of reads happening from the front end applications, but the write workload far outweighs the read workload. So our latencies on the front end are mainly driven by how much data we're absorbing. And trying to control that, or trying to cap that is probably going to help us with latencies. Another thing, if you remember, I mentioned that the EMR jobs tend to generate very peak load. So, we might be observing, let's say, 10,000 average writes, but really it might be that for some time we're seeing, 2,000 writes per second, and then suddenly we see a spike of 30,000 writes per second, because just at that point some EMR job came in and started syncing. So our average latencies might be decent, but it affects the TP99, TP95 values a lot. For backend, one of the biggest issues we faced was that when we switched EMR jobs to talk to Cassandra, Cassandra is a relatively fixed resource compared to the EMR. EMR is basically elastic map reduced. You can launch as many clusters as you want and very easily scale if you want to run just bigger data sets. But the same is not that true for the backend data center. So what happens when you throw a very easily configurable, very easily scalable system against a fixed resource? You can pile up EMR jobs and just very easily overwhelm even your largest cluster. So we can double the size of cluster, triple the size of cluster, but the EMR jobs, you can just very easily keep growing. Now, we tried social engineering. We tried to figure out what our capacity is, try to make sure nobody exceeds that. But when you have lots of applications, a lot of jobs running all the time, and the granularity is at a job level, it's not easy. It's not easy for the developers to be able to control their load. It's not easy for one team to know what the other team is doing, and we can't be expecting people to simply coordinating our email, figuring out when can I run my job. So that was a no-go for us. Another issue on the similar side is that in this shared environment, when we work with multiple merchants, so we have large merchants, we have small merchants, and we have some applications which are very large applications, they operate on the global data sets. There are other applications which operate on smaller data sets. They have tighter SLAs typically. Larger jobs have relaxed SLAs. But when a large job comes, it can easily load the system, the data center, and starve out the small jobs. And we miss the SLAs on that side. So this is roughly the set of issues I'm going to talk about. Front-end isolation is not that perfect if you're relying on multiple data centers. Front-end latencies are impacted by back-end write load if your writes are if your write heavy workload. If your writes are not that many and you're mainly read heavy, then I don't think you'll have this problem. EMR jobs can very easily overwhelm any Cassandra cluster. And of course, large EMR jobs can starve the smaller ones. So the first solution we came up with was basically a rate limiter, which was, okay, we have a fixed resource. We can't simply allow an arbitrary large set of EMR clusters to come in and overwhelm the cluster. This was based on a token server. It's basically a standard token bucket. We do code allocations. The nice thing was that we went to the QPS level. We went to actually operation level. So we could say that, yeah, you're allowed this many scans, this many reads, this many prepare, all to create. We basically build a layer around the data stacks driver. So every application needs to get their quotas. And now we could control that. We knew for once that what is our capacity of the cluster that we're running. And if I can afford 300 scans per second, then on a neat basis, we can say, well, this application can have 50 QPS and so on and so forth. And the applications themselves can realize that if their jobs are sitting idle or waiting on the quota, then they're running too many jobs, and either we need to scale the cluster or we need to run the applications at a lower level. The rate limiter is basically, the design is around the Guava rate limiter, but this is more of a global rate limiter. We're talking about multiple map producers across multiple machines, and all have to synchronize among themselves. And of course, we dynamically adjust the quota, so if some application is not using their quota, we make sure it is still used by other applications who are running. We chose Redis to run this rate limiter, the token server, mainly because the main requirements were, one, there was still high enough load. Even though we're not querying this rate limiter, we're querying it at about a minute per mapper, but still the number of mappers and reducers across all the machines can be fairly large. You can think about like 100,000 or more clients connecting at the same time. We want very low latencies. We don't want this thing to become the bottleneck in our scalability. So we want very high number of concurrent connections. And of course, we want to do the atomic fetch and add. That makes it easy to do the global counting. We considered multiple solutions. We tried MySQL. It fell apart pretty quickly. We thought about using Cassandra counters, but we thought it was a bad idea to protect Cassandra with Cassandra. So using another system gave us a little bit more confidence. And lastly, Redis is an in-memory database, and it worked really well for a lot of those cases. So we got the rate limiter. Now we have our cluster safe, but one thing became plainly obvious. Elastic MapReduce is not elastic anymore. We have a fixed MapReduce. So if you want to scale with EMR, if I have a large job that takes a day to run and I want to run in 12 hours, I can't double my EMR cluster size anymore. I have to double the Cassandra cluster size. Now Ben talked I don't know how many of you guys were here in the last talk, but the last talk Ben talked about how to add node to Cassandra cluster and how to make it easy and make it possible. But as it stands now, it's not that easy. You can't add new nodes to a cluster in matter of minutes or matter of hours. In our experience with the cluster we're running and the amount of data we have, adding nodes is a couple of days operation where we take our sweet time, carefully add nodes, observe it, watch it. Adding capacity under heavy load, we had very mixed success. When EMR jobs are running and the system is operating at 50%, 60% CPU usage, we try to add nodes, they mostly fail. And that leads into some bad situations where we had some nodes that just became phantom nodes refuse to join, refuse to go away. So in our experience, we have to cut down the load significantly on the cluster before we can join the nodes. Now that has been a solution for us for a while, but it affects my availability. One of the things I mentioned in the beginning, that we want always available. I can't ask for a maintenance window because, well, these jobs, they process a lot of mission critical data, and I can't tell them that no, you can't run the jobs now. And lastly, if I want to auto scale, like EMR is very easy. With the script, you can scale very quickly, very fast. And if I want to do something like EMR, then it gets even harder. So how do we manage the capacity? One, from our point of view, the requirements is around the time to increase capacity should be measured in minutes. It should be programmatic, should not be manual, should not be an ops work item. And at the same time, when we're doing it, there should not be much load on the production cluster. Now, when you add a node to an existing ring, what that means is the existing ring has to be, the token state, the token ownership changes, so all the data has to be reshuffled. Now, imagine if I have, let's say, 100 column families in the cluster, and I want to run an EMR job which wants to operate on one column family. Then if I want to scale for that EMR job, I'll have to pay the price of shuffling all the data of all the column families, and that can add up a lot. Now, I think there are ways that we can reduce the overhead. I would recommend, if you're interested in this, check out the slides from the last talk. They used a backup service to reduce the overhead on the nodes, but still the same problem exists, that adding nodes to existing cluster means you're reshuffling the entire data set, and your jobs may not be operating on the entire data set. The solution we went with is, if we have the new nodes, we can just build a new cluster. And we're not really looking, let me rephrase this one. If we are mostly interested in reads and not writes at this point, then for reading, we don't need to increase the size of the cluster. We don't need to add more shards. We need to add more replicas. And that's how we get our capacity. So if I add a new Cassandra cluster and replicate the data I'm interested into this cluster, then from my point of view, I have increased my read capacity without reshuffling any of the existing token rings. So to do this, we built a custom replication service. We installed the replication service on all the source nodes. It operates right next to the Cassandra. On the destination cluster, we have the same replication service running over there. The general idea is basically the column family you want to replicate. We copy the SS tables over the network onto the destination nodes. On the destination nodes, we figured out what the new SS tables will look like, because the token ring has changed, so the SS tables don't apply as is. You have to recompute what are the new SS tables going to look like. So we split the SS tables. Each SS table gets divided into another n tables if we have n destination nodes, and then we stream the data over. And we try to do all of this in parallel. The splits, the file copy, the loading to the destination nodes is happening right in parallel. So this one is basically talking about the replications service, which is we converse with the Cassandra node using the JMX protocol. In between the replication service, we're using the Finagle RPC. Roughly, I think I already went over this. So replication service, we take basically a snapshot of the column family using JMX. SS tables and snapshots are evenly streamed. Then we split the SS tables into n SS tables, and the splits, we compute the splits using SS table reader and writers classes that are already part of the Cassandra system, so we didn't rewrite any of that part. We just reused the code that was already available. And a lot of our effort went into doing all these computations as much in parallel as possible. And one of the reasons actually we chose to do all this computation on the destination was the destination cluster is something that we can choose to arbitrarily increase, because that's a brand new cluster we're building and it doesn't take much time. So if I want to run something in half the time and I want to reduce my time to to replicate, then I can simply build it twice the size of the destination cluster, getting me twice the CPU and twice the disk I have and all that is needed. And I can cut down the time it takes to do this half. This half, of course, is limited by the disk and the network bandwidth that the source cluster has. So once we have computed the splits, and once they're streamed to the correct destination nodes, to get the cluster to recognize the new SS tables we dropped, we basically do a rolling restart of the cluster. We could have used the node tool refresh, and actually we did use node tool refresh, but in our experience it wasn't as reliable. There were times when we discovered that the SS tables were not picked up and the data wasn't consistent. But rolling restart is fairly straightforward operation and almost always it guarantees that the data is always correct. At this point the cluster is ready to use, but however the SS tables are severely fragmented because we just computed splits from multiple nodes and we did not bother merging them. At this point, we basically trigger a compaction and let the Cassandra come in and merge those SS tables to optimize reads. But from our point of view, the ML jobs can come in and start using it. Initially, they'll see a little bit performance impact as do the scans, but as the compaction catches up, that performance impact goes away. For cluster provisioning, we start off by estimating, we basically expose a REST API which takes in a column family that you want. Rest we just compute based on that. So we'll figure out what is the disk size needed for that column family. Based on that, we figure out what are the right machines from AWS. We have already, Cassandra is already pre-installed, so there's no setup involved. All we have to do is generate a YAML and a topology file. We still create a backend data center. There's no really need to create a backend data center. This is a single cluster with a single data center, but one of the goals we had was to make sure that the applications are completely unaware so that we don't have to rewrite the application code. And to application, the only thing that changes is the set of nodes it talks to. Everything else is the same. We copy the same schema from source cluster, destination cluster, and then call the replication service. So an application that was operating on the production fixed resource, when it gets this new cluster to it, there is no difference. The only difference is that you're operating on a snapshot. You're not operating on the live data. And that's, as long as that doesn't affect the functionality of the application, the system really works. So what do we have now? We have a source cluster, and we have the ability to generate lots of on-demand clusters with replicas of data from the source cluster. And we can tie that with the EMR jobs in whatever mechanism we want to do. So what do we get from this? We noticed very high throughput in moving the raw data. So if we're just copying SS tables as a simple file copy, we noticed our cluster, which was when used through EMR jobs to do scans and lookups, versus when we try to copy the data out by just file copy, we saw almost 10 to 15x, actually I said 10x here, 10x increase in the network usage. So what that meant was that even though we thought our cluster is not capable, but really from a network and the SSD disk I/O point of view, we had a lot of capacity sitting idle, and that was just untapped. And what we were getting bottlenecked on was basically the CPU and the JVM doing all the processing that it does. During this process, there's literally no CPU or memory load on the source cluster. And that's the part that gets really heavily used when we add nodes. So this keeps us flexible from changing our original source cluster size if we need to. We're really leveraging the size of the destination cluster, which can be arbitrary, can be fixed, or can be decided based on the workload that you're running to compute the new SS tables. In our experience, time to provision has varied between 10 minutes to 40 minutes. 10 minutes is almost the time. Out of 10 minutes, about 7 minutes is what it takes us to provision machines from AWS on average. And so really, for very small merchants, for very small column families, the replication time is hardly noticeable. For very large column families, roughly talking in the terms of, let's say, 300 million records or something, or 400 million, or close to billion records. It can take anywhere from 30 to 40. And this time is split almost half and half in terms of the network bandwidth that you have on the production, and how much the size of the cluster that we built on the destination. This is completely API driven. By API, it's a REST API. You can simply call from the application point of view. There is no provisioning. All they do is say, I want to operate on this column family, and then you wait 10 or 40 minutes and you get your cluster to work against, and it has the same production data. So from application point of view, it's usually the integration involves 1 or 2 lines of code change, and that too on the launch scripts or the Python scripts that manage the EMR jobs. So what are the limitations for this? It's not an answer to everything. It's basically a snapshot model. We take a snapshot of production data and we let the jobs operate on it. So this works really well for some use cases. We actually discovered some of our applications benefited from this because they were doing global optimizations, and while they were doing global optimizations, they made assumptions that the data won't change, and when the data changed, the optimizations were not really as good. So in the snapshot model, they got their own copy at a particular time, and those optimizations improved. It's good for most of our use cases on the back end, but it's not for all use cases. You can easily imagine use cases where you can't really work on the snapshot. You may be operating in conjunction with a front-end application that is modifying the data as your job is running, and then this can aggravate existing race conditions, although those race conditions may not be that obvious in a normal EMR job talking to the Cassandra, with the front-end application talking to the Cassandra. So we had some of those cases, so not all of our applications could be migrated to this model, but most of the heavyweight applications we were easily able to migrate to this model. Provisioning time is still order of minutes. So it works for EMR jobs because EMR jobs themselves take a few minutes to provision. But it won't work for let's say, a dedicated backend application which was constantly processing some feed and the SLA is below, let's say, 5 minutes or something. Then this solution doesn't work for those cases. The good thing is those cases usually, when they provide such tight SLAs, you're not talking about very large amount of data. So it's easy to react to those at least. And you're not in the EMR world at that point. And lastly, we solved a read problem. We didn't really solve the write problem. So writes still need to happen on production reserve cluster. So where did this end up? So we ended up in a situation where we have all the reads happening on this on-demand clusters, which we are replicating. We still have a token server and a rate limiter. We apply that only to the writes that are going on over here. And yes, so now we didn't actually, when we built this thing, we were trying to solve simply a scale problem, but then we identified that there are some advantages to this that we can exploit further. One is that what we really built is very easy way to automatically, provision a new Cassandra cluster with production data on it, and we can do it reliably. And we've been doing it reliably for a while, and very little, actually no operations involved. It's all automatically driven. So what that gives us, instead of using on-demand instances, we can use spot instances from Amazon. So I don't know how many of you are familiar with spot instances. Quick show of hands. Okay, so let me give you a quick idea about spot instances. Amazon has this nice feature where you can request machines at a particular rate on demand, and they charge you some money. On the other hand, they have a bidding system going on where they're saying that we have this pool of machines lying around. They're called spot instances. Their price is dependent on a market price decided by demand. On average, they cost about 1/10 the cost of an on-demand instance. So very, very cheap, but no difference. It's the same instance. It's just a pricing strategy that is different. There's one catch, though, which is you get to define a bid price. And if the demand increases enough, that raises the market price of that instance beyond the bid price that you put in, then you lose that instance right at that point without any notice. So spot instances are very cheap, very good, but you can lose them at any given point of time. So You can use them in environments like, let's say, if you're running a long analytics job or an EMR, and if it dies, no big deal. But trying to run that on a database, we never even thought about that. But if you go back to the model we're operating in, we're saying, well, if you lose a cluster, no big deal. We can bring up a new cluster in a matter of 10 or 40 minutes. So if your SLA is relaxed enough that you can survive 10, 20 minutes outage, then we can use spot instances, and that has a severe impact on our cost. Also, we have Cassandra redundancy, so we can leverage some loss, and if there are too many failures, we just rebuild and retry. And we're using spot instances for all these cases, and in our experience, we have had some failures, but not a lot. And actually, I'm going to talk a little bit about that. We have run some clusters for almost a month, running completely on spot instances without any issues. So one of the first things we did was we made sure that the service that provision these clusters can support every single instance type in AWS, and we can work on any availability zone. It did meant that we built multiple AMIs, and we support multiple virtualization technologies, and run our tests, and ensure that Cassandra can work on all these different instances. Another thing we did was, one of the mistakes people make with choosing a spot instance is you say, I'm going to operate on C3 2x large, and then you hard code that value. The problem with that is you don't know what the price of it is going to be, and the price can spike. When the price spikes, it can last for days. Maybe people in the Large Hadron Collider started running something on C3 2x large, and now for the next weekend you can't do anything. So what we do is we constantly monitor the prices on the spot instances that Amazon has, build a sort of a statistical model, and figure out these are the ones which are more stable in pricing, and they are the cheapest. So given a particular constraints of a cluster, we know this is the disk that you want, this is the memory we want, this is the cores we want. We find the cheapest spot instance that is available, and then we use that. This, of course, reduces our cost because we tend to operate on a cheaper spot instances than the more expensive ones, but it also improves the reliability. And the way we improve the reliability is that, let's say we were using R3 2x large and the price spiked. On retry, we're not going to pick R3 2x large. We're going to pick something else. And in our experience, there's a decent probability of failure the first time. The probability of failure the second time is independent of the first failure. The probability of failure the third time is even independent of the first two failures. So the overall probability as the number of failures mount decreases significantly. And in our experience over multiple months, we haven't had to do a third retry. On second retry, we always succeed. Lastly, we auto-expire clusters on our own. If you find there are cheaper instances, we just kill the clusters ourselves. Rough numbers, we noticed that for the same dollar value, we got almost 5 to 10x more capacity in terms of throughput, random lookups, and scans. So far, I've addressed the backend read capacity and front-end latencies that are competing with the write load. But the issues that I haven't talked about yet, one was that there is a read load on the backend data center that can spill over to the front end. And then there's a write capacity that is still defined by front-end latencies. So this was the issue I was mentioning. Part of this problem is addressed by having that rate limiter, which can ensure that we never have this situation where you have so many nodes overloaded or gone bad. But if we wanted to guarantee, we didn't want to rely on this. We actually did a little fix in the Cassandra code itself, where we could say that this data center don't use any of the replicas from this case. And that gave us a little bit more assurance that if a situation like this arises, the outage is reflected only on the backend data center and doesn't translate to the front-end data center outage. The write capacity, there's an obvious change we could do, which was that only push the updates that are new. EMR jobs, you tend to scan everything and write everything. So you may not have changed everything. We want to do this from day one. The problem was that if I have to know whether it has changed, I need to read the value first. And then you have this decision to make, which is more expensive, writes or reads. And in the beginning, reads were just as expensive as writes. So doing a read to save a write did not make sense. But in the snapshot model, where the reads are on these spot clusters that are almost free for us, this wasn't a problem anymore. So we started doing this, and we discovered that almost 80 to 90% of our data doesn't change. So it's not increasing the capacity of the cluster itself. It's a sort of an application level change, and it depends on the use case. At least in our use case, if the application was doing 10,000 writes per second before, now with the same 10,000 writes, it can do 100,000 writes per second. So applications saw some effective improvement. Another option is we can add more nodes with the backend read load. And with the backend read load off, we can do it a lot easier than we could do before. But we're still operating at about third or fifth of the write capacity of the cluster. And when we observe our front-end data center, we see that it is very lightly used, and we're deliberately keeping it idle just to improve the latencies. This part is we're still experimenting with this, which is one, we're trying to figure out if it's possible to prioritize the reads over writes on the front end, something like pause the write stage during a read and see if we can get better throughput. Second is if we can reduce the replication load on the front end from the backend data center, and we're toying with an idea around column level replication, where it's more of an observation, at least in our use case. I don't know how common is that the front-end applications, they tend to operate on a subset view of what the backend data set is. And right now in Cassandra, when the replication is at a key space level, all your data gets replicated to front end, even though you may not need all of it. So we toyed with the idea that maybe we can build a front end view and a separate table, but that doubles the writes on the back end. And also, the views can keep changing, and we can't keep changing the data model that frequently. So in this strategy, we're thinking of reducing the mutations to the front end by filtering out the data that doesn't go. But this is more of an experimental change. I wanted to just throw it out. And we have it in a test environment. We don't have the, we saw some benefits from this, but we don't have good numbers. And there are a lot of open questions around what does it mean for repair and for adding nodes and consistency in general. So the key takeaways are we can scale Cassandra dynamically for backend loads by creating snapshot clusters. We use rate limiter to protect the production cluster from spiky, unexpected traffic. We can build better isolation between the front end and the back end. And for us, write throughput still remain a challenge. So that concludes my talk. Thank you so much.